my name is Kevin Kocek. I'm the founder CEO of Chemical Q Device. We'll have more people coming in here as well. So kind of where we left off last week is basically, with imaging, in specific fluorescence, all the different types of fluorescence. And this is going to be some overviews of some papers and then getting really into quantum imaging. So quantum imaging is quantum sensing, ghost imaging, you have lithography, and then sub imaging as well. So as you can see here, so some of you have seen this. This is the overview of what's going to be going on today. Literature reviews in Alzheimer's disease, PET tracers, CT, MRI, new quantum sensors. So these are basically mostly diamond quantum sensors, if not all, and just what's being built up around them to make them even better. As you know, they're you could put them in any type of, it's basically diamond. And for temperature, for a bunch of different readings as well. And you see this, so more noise imaging. So subshot noise, ghost imaging, and lithography. I'll go over those a little bit later. So for those that haven't seen this before, this is the electromagnetic spectrum. You'll hear the terms, so you can see radio, micro, infrared, mostly going to be talking about fluorescence with diamonds. So that's green to red, that transition. And then you'll hear a lot of these kind of milli, micro, nano, pico. So these are the prefixes that are used. Some of the abbreviations, the PSP and the CBD, these are specific things, save for Alzheimer's, dementia, and then, a lot of these other ones. I'll use NV a lot. So inside a diamond that has these vacancies, it's a nitrogen vacancy. And then linear dynamic range, signal to noise, and quantum information. So if you're new to this, within the past couple weeks, I've been sharing this every week. It's basically very important for medical imaging processing steps. So these are all the steps involved. So you'll see data acquisition, and then in this step, detection, which is sensing, conversion, preconditioning, and we're talking about the raw data. And then reconstruction, you'll hear a lot with algorithms and specific. Some of the quantum imaging, such as ghost imaging, it's known to be slow in reconstruction. And then you also see things, so enhancement, analysis, visualization, that's more computing steps, and then management, communication. I'll touch on that just a little bit. Now, for those of you who have taken biochemistry before, it's been a little bit updated. So as far as I know, this is the most recent kind of, big picture in all this, where you have amyloid beta plaques, and this activates microglia, cytokines, and then, basically you have two different types of tau, extracellular, and then tau being released to neurons as well. So this is not an isolated event where you just have amyloid beta plaques forming, or you just have tau tangles inside, neurons. It's a comprehensive thing, and this was in Nature. The first paper I'm going to look at here is basically neuroimaging has become the forefront, and in many cases you can actually have a very clear diagnosis just by looking at the images. I'll share a quote with you that's coming up as well, but basically you can you can sense the level that a particular area of medical is in based on their imaging, how clean their images are, these types of things, because that's how you see things. Now, a lot.
Only thing Spider-Man's doing is sitting at home jerking off. How are you a superhero? Fucking loser, Spider.
So a lot of these things is basically, you see many studies have been done. And it's basically everything's building up with imaging to this day. So the whole goal in a lot of this is basically to get longitudinal studies, and this means same patient. So this is a PET scan, and then it's basically a glucose derivative that you take. It's basically glucose without an OH, and you put a fluorine on it. Now the red areas in specific are the ones that are interesting because it's low metabolism. So this was done, and this was actually, this paper, it's a 2022 reprint, but it was originally made in 2009. So it's just interesting to see that a lot of the quotes that they use in that specific paper are coming true. Now in the second paper here is, you'll see these in PET scans. So if you take MRI of just if you go to any hospital, it's really hard to see cancer. It's hard to see lots of things because you just don't get that contrast. So I talked about, these amyloid beta specific tracers. Now, the whole goal with this, in this case, is you want to get PET tracers to go with it. There's only a single PET tracer at the time of publication, and this is a 2022 article in NIH. And there's been a bunch that have come out. I think Genentech has one, but they're not for clinical use just as of yet. So you see this, so it says 6 second generation PET tracers. And then say, for instance, this is one of the PET tracers, and then you always try to have these binding models. It doesn't always go this easily, but it's just the easiest way in our heads to basically say, okay, this new PET tracer will perform better, contrast in these brain images that you see. Now, getting into basically all this falls under quantum imaging. So when you're talking about classical versus quantum, you're talking about in the quantum entangled photon pairs. Now, in 2015, this is a surprise to many people, is that these diamond quantum sensors that I've been talking about for the past several weeks have been used to, look into advancing MRI. So some of these studies are kind of, preliminary, just Teflon, organic polymers, and then proton, fluorine, phosphorus 31. But these things have been done for a while, and it says it will certainly be exciting to watch the progress in this field and see whether these defective diamonds will sparkle brightly as research tools. Now, if you just watch the headlines, you would think that quantum is an industrial initiative. It's not. It's a government initiative. Since the early 1980s, NSF, the second one here, has basically been funding certain aspects of quantum technologies. Now, so these diamonds with nitrogen vacant centers have been known to have hyperpolarization, basically have a great effect compared to other quantum sensors. And they've used it in NMR, which is basically MRI, but for analytical chemists. I talked about this last week, the scanning confocal microscopy. So there's all different types of hybrid things. Now, one of the big benefits is basically you can use this for single cell imaging and also for detecting single neurons. If you want to learn more about a lot of quantum sensors, and especially diamond quantum sensors, I would highly recommend this, Bringing Quantum Sensors to Fruition. It's free. It's on quantum.gov. And these are the organizations that are involved with this in specific diamond quantum sensors. Now, more recently, there was a paper done. It's not in vivo. It's not a mouse's brain, just open brain surgery, that kind of stuff. But it's basically taking a section of the brain and stimulating it, and then using fluorescence in this diamond quantum sensor to measure activity off of it. So this is very interesting. So if you were to go away home with anything from tonight's talk, it's basically diamond quantum sensors are be using for very close distances to the samples that they're measuring. So they're not always 100% the best signal to noise. Say, for instance, like a squid MEG, or sometimes even OPM MEG. But that's been the thing, is that they're biocompatible, meaning they can be placed up against subjects. And you'll see a lot of these things. So this paper in specific it's an archive paper, but they kind of beat a lot of people to the punch, as far as I know, to just get something going with brain and neuron and diamond quantum sensors. And you'll see one of these electrodes is for stimulation, another one's for recording as well. And again, fluorescence, just like last week's presentation. Now, this kind of surprised me in a really good way. ACS, and this is a 2021 paper, basically they said you could use it for all types of biomedical applications. So carbon or diamonds are basically inert to everything. They're super hard. Now, we're not talking about large diamonds. We're talking about nano diamonds. They don't need to be huge. So, and things you'll see intracellular temperatures. There was a gentleman last week that asked a question as far as like, you know, can this be used on cells? And it looks like yes, it can, or at least it's in the works to be. Now, the article that I've been talking about the most is last month. So if you were to look at all of this diamond quantum sensor, the business behind it is in 2009, NIST said that we could possibly get these small enough to put on a tip of a rod and use it as a little MRI. And then 2021 last year, they figure out the algorithm. Now, the paper that's probably the most comprehensive as far as, taking 4 individual rats, doing this diamond quantum sensing on all of them, comparing it to the next up quantum sensor, which is OPM MEG, is that it seems to be doing, in specific this paper by Arai, K, and L, it seems to be maybe the one that's kind of taking it the furthest. And in fact, they say what needs to be done next. So they achieved the better magnetic information recording than OPM MEG, although it doesn't have as good signal to noise ratio. The fact that that it was placed a lot closer to the heart in this case was the big intrigue. So you'll see things. So basically, they're saying what to do next, and this is good for any research. Is basically using parallelization with CCDs, or perhaps even an EM CCD, like we talked about before, CMOS instead of diodes. Now it's just a really extravagant, it's beyond, well, I don't know how exactly to put it. So full vectorization of magnetic sensing by all encoding classes of NZ centers. And basically the whole goal with this is to see this in hospitals. This quote here is very key. It says, our technique will enable the study of the origin and progression of various cardiac arrhythmias, including flutter, fibrillation, and tachycardia. Now, these researchers here, it's a Japanese researchers, and last month was a huge month for them in August, basically for quantum computing. And in specific, it looks like they're going after a lot of the medical stuff. So here's the diagram here. So you can see from bottom up, heart, microwave guide. The microwave guide is basically, you have these spin states that occur within this nitrogen vacancy diamond. And you want them to either be, typically they could be up, up, down, up, or down, down. So you typically have it, so it's, having it, the spin state stuck in up, down to get this hyperpolarization. And then you can go see, so they talked about a photodiode. So there's basically, this is their standard setup that they had. And, like in the previous slide, they're listing specific things to improve. Now, this is kind of where the rubber meets the road. So like I said, and I'll get to the data with it, is basically, this is using optical measurement. In B, so this is the NV data off the diamond sensor. And then in C, it's OPM. Now, OPM in this case was found to have a greater SNR, signal noise ratio. However, since the diamond could be placed closer in this specific application, now you see clear blue, clear red. And then an MRI was needed in order to fit these. And then you could see after it was fit, the resulting vector is larger. You could see more clearly what's going on. The circle is smaller too, and they get into more detail, but that seemed pretty good as far as having something that looks better than the current generation in quantum sensing. Now, the OPM MEG, like I said, you can see the signal to noise ratio goes up from 10 to, this looks like logarithmic. I can't tell if it's 50 or whatever, but it flattens out. And then the rat A, B, C, this blue, green, and red are basically with the diamond quantum sensor. So the signal to noise ratio is not as good. However, the overcoming factor here is you see the standoff distance where the sensor is placed on the heart, is that even though it doesn't have as good SNR for this generation of quantum diamond sensor, is that now you're getting magnetic field, the higher the better. So you're up in nanotesla, where the previous or the kind of the current gen of the OPM MEG is in picotesla, which isn't quite as good. So another big one here, and this is with China too, is basically mixing. So this, if you want to look this up, so MIT and these Chinese researchers basically claim this year, I think maybe June, July, that using this frequency protocol, Rabbi or CPMG with a quantum frequency mixer, that you can detect any frequency. So they too provided, and I'll show you the information as well. Now, their future direction is to integrate their mixer and sensor with masers, which I believe are microwave lasers, to enhance sensitivity and frequency range. And again, a lot of these things are continually being developed as far as what's being built up around, the diamond itself. And like with anything, it needs improvement. So what to take away with this is basically you have the laser, and it's this mixing that they're doing. Rabbi and CPMG are sequences, and the readout is reference or signal. So in this case, they're saying that you can use this for other applications as well. This is very interesting. So this is quantum-assisted distortion-free audio signal sensing. Now, the thing with this is they call it the quantum phase sensitive detection scheme, QPSD, and they also use a heterodyne readout. And basically what it says is that, unknown signals with maximum sensitivity, and then it improves the feasibility for, nitrogen vacancy, diamond magnetometers, and other qubit sensors as well, to get extended linear dynamic range. Now, this quote is very interesting as well. It says, "We envision that the techniques developed here lay a path for different quantum sensing platforms in achieving low distortion sensing required for many applications in science and technology." So the one from MIT, which is more mixing, and then, or it is mixing, and then this is their thing, is if you read this paper, you can actually see some clips. So they say one was Melody, which was just a basic clip that had noise, and they removed the noise. The other one was the Martin Luther King, "I Have a Dream," and then they removed the noise in that as well. So this is the data that goes with it. So the takeaway here is basically when it says QPSD Ramsey, is that it's better than the previous. So as you can see below here, how it QPSD Ramsey and the X's continue linearly, where Ramsey falls off. And then similarly for QPSD Han Echo, is it's linear here, where it falls off, and it seems to actually go back to its baseline right there. Now, this is basically the setup. So it says to perform the QPSD readout, this is how everything looked. So you have these pulse sequences, laser. So it's fluorescence. All these tend to use fluorescence here. And then if you want, you could look into the paper more, but that was kind of interesting. Now, basically, there's artificial intelligence being implemented with this. This specific paper is for ML. And they're basically saying that, using machine learning, it's another crux to make these diamonds better. And we're talking like the readout, last year was huge in getting the algorithm down, and then it's just further improving things as far as saying work opens up possibilities of ML for accurate quantum sensing. So this is the setup in this case. And basically what you want to look at is optical is Z, up and down, and then this nanodiamond ensemble is what they place in the XY axis right here, is right there. And this is what they're using with machine learning to get better results for these quantum sensors. So the spin amplification is basically saying, this is probably one of the more technical ones that's out there, is that it's saying a system with a highly imperfect spin readout has the ability to approach quantum limit-like sensing. So it's all these different techniques that these different researchers are going about to get better signal to noise ratio, better sensitivity, and ultimately better resolution. And here in specific, so the Ramsey sequence is familiar, and then this in specific where it says signal amplification and readout is what's being done in this paper to, basically get, certain aspects of the better sensitivity. This one is kind of surprising. So this is a smart quantum camera with AI. So in case you missed it to begin with, quantum imaging is quantum sensing, and 3 other ones that I'm going to get to as well. So in this case, it's basically saying that the whole point in using quantum is to break through limits. So in this case, the limit here is the Abbe-Rayleigh resolution limit, and it's defined by Heisenberg uncertainty principle, the quantum aspect of it. And then when I get to subshot imaging, I'll show you as well, as far as there's diffraction limits. There's basically reasons why people want to use quantum. It's hard. It's hard to get this down as far as having it reproducible out in industry as well. And then, so what's interesting here is basically, if you read through the paper, is you get these 3 light sources, and I don't have all the abbreviations for DMD, but ultimately what's happening is that the neural network is taking a look at these 3 different light sources. So when I get to ghost imaging, where it has 2 photons split into 2 different paths, and then one gets detected, and then one sees the object, but they're still both entangled. It's this spooky action at the distance that Albert Einstein described in the quantum world, that things just act different. So I was talking to a colleague today over lunch, and he was talking about imaging microscopes. I said, oh yeah, there's a diamond voltage imaging microscope. And this was mentioned basically, earlier with the other, president of the US, and these quantum sensors coming to fruition. So basically, it uses some existing techniques, and then, but they're limited in certain things. So that's why you need this new optoelectronic voltage imaging system to overcome these things. And then in specific, you'll see this a lot, is that everybody wants label-free large scale and, a long-term voltage. And and especially, biological systems tend to be harder, certain pHs, these types of things. But since the sensor itself is, it's diamond, is that it's biocompatible with pretty much everything. So another interesting one here is basically the nanoscale electric field sensor. So this is basically AC and DC electric fields. And then it's good, the articles that, and this is a Nature article here too, is that they want an atomic force microscopy, so it doesn't actually touch certain things, recalibrating the probe, using, and here's a big thing as I get to kind of like batteries in these diamond quantum sensors, is to use multiple nitrogen vacancies of different orientations or multiple pillars with MVs, and to use shallower NVs as well, and motorized goinometers for better control. And interesting quote is, they say, integrating electrometry and magnetometry into a single scanning probe will open up exciting possibilities in imaging nanoscale phenomena. And here's what these look like. So here's your magnetic field, quartz substance, microwave strip line. Is you always see that, like, we'll have fluorescence, so green going in at higher energy, and then red coming off, and basically the goal is be able to read the red a lot better. And in this case, they actually use the diamond, like, so if you look in the lower right hand corner with the image, it's that bottom tip is basically, they say it was pointing up, but it's in a certain alignment. It's basically moving these diamonds around, getting more arrays of diamonds. We talked about this, I think last week, if you can have single ones or arrays. Now here's the robust battery monitoring one. This was in Nature as well. This seems pretty legitimate, and it's basically saying current day batteries, you can only get about 10% accuracy with the exact charge state that it's in. Now there's always the headlines that come out with it. It seemed like it may be down to 1%, but I think their quote at the bottom kind of like, captures everything. It says, increasing 10% battery usage efficiency reduces 10% battery weight, which will reduce 3.5% running energy and 5% production energy of 20 million new EVs predicted in 2030. And they went on and on for this carbon dioxide calculation as well. But it's a pretty good paper, and it's a very interesting setup, because you'll see in these other ones that I cover, basically they're talking about different orientations of the diamonds. Well, this one uses 2 diamond sensors for differential detection. So without not fully understanding everything about this and batteries and all this kind of stuff, it's an interesting setup. And a lot of times breakthroughs come by watching all the other diamond quantum sensor news, not just for medical as well. This one took me by surprise, because CMOS and quantum sensor, this was basically 2019. And what it is basically NV-based sensing with the CMOS. So CMOS is a very familiar detector in imaging, cameras, all this type of stuff. And they say it's likely compact and scalable. I haven't seen anything else in nature on this one after 2019, but it's very interesting to see, because a lot of people think with the quantum diamond sensors is that they're not just going to be just for themselves. You're going to see hybrids, and here's, for instance, a hybrid with CMOS. And then so you see the NV in the diamond, and then this specific ray with microwave generation. And then quantum imaging. So this is one of those, you really have to just sit down and take your time with it. And it's basically in ghost imaging, it starts with a photon pair. And then, as I'll show you in the next slide, one photon is going off and seeing the object, the other is seeing a detector. However, they remain entangled, so one still senses the other, even with it not even being there. So they use ghost imaging. The main limitation with ghost imaging is, I covered this kind of in the medical imaging slide, is that the reconstruction is really slow. And the goal is to get the highest resolution and the shortest acquisition time and for this. And it's used for low photon fluxes and non-degenerate object image wavelengths. You'll see a lot of kind of dark images that it can pick up pretty well. Now, here is the setup. So this isn't solving ghost imaging. This is basically saying, we're going to use neural networks on our noisy low-res image because we can't get a higher res image at this time. And then you could see the beginning and the end with this. So noisy low res to begin with the neural network, and then afterwards. So it's really quite an interesting thing, and this is tying into other aspects of, say for instance, entanglement and quantum computing. But on the left is basically, you want to look at, so where it says 2, where it says mass, those are where 2 separate photons are. And then they travel through, and then you go through all this other stuff to get your noisy low res. And this is basically saying, this article from 2022 is dealing with this noisy low res image, because that's the issue, is reconstruction. Now, reconstruction is tied in with algorithms and whatever it takes to run those algorithms. So in the later days, for detecting dark images, that maybe it's possible to get this noisy low-res image quality up. Now, the subshot noise imaging is seen other applications. Actually, in the lower left-hand corner, you could see this is before. So it's basically, if you have, they use for absorption in chemistry. If you have a shot, when you're using quantum properties, you go below the shot. So that's called subshot noise imaging. And as you can see with the subshot, the results, basically taking off some of those red peaks, and it's just not quite as tall. And they said in this article, and this was this year, is noise suppression by as much as 30% below the shot noise limit. So this is talking about diffraction limits. And then we talked kind of about the Abbey, the other one before. It's like there's certain, things that in the quantum world that you can go below what's being done classically today. And this is another interesting thing too. So I want you to take away with this is basically, if you could see my cursor here, it says left and then reference to the right. This is 2 photons. So there's a photon on the top, top rainbow, there's a photon on the bottom rainbow, okay? It hits this reference, and then you see the bottom photon here has a different path from the top photon here. One goes through the sample cell, the other one goes through these other things, and then you see that they're recombined. So top rainbow, one photon, bottom rainbow, second photon, and here, and sensed within a CCD camera. Now, the one aspect, so you can see that basically the review here is in quantum imaging, you have sensing, which we talked about a lot with diamond quantum sensors, subshot noise, which we talked about ghost imaging, and then the one that's kind of hasn't really picked up much steam, and this is a 2000 article, is called quantum lithography. So there was debate 10 years later, 10, 11 years later, as far as, you know, its practical use, and is it even better? So it's a very specific thing as far as the physics between all these. The good news is it's possible. This is actually an ACS article to have membranes, and keep in mind, you don't have to have nitrogen vacancy. You can have silicon vacancy. So I think that's just silicon, and then you have 2 vacancy. Now the key in all these is basically the place where the green laser and red laser are coming off. It's the hyperpolarization. It may as well be normal diamonds typically have 1% nitrogen, and then that might be how all this got stumbled upon. So there could be other different formulations in diamonds as far as different elements in the periodic table that could have you know, greater you know, potential than that. And then this is basically a crude thing that they use, but if you look at the elements, obviously helium, germanium, nitrogen, palladium, tungsten, and then in D you see some polymers, polycarbonate, PDMS is silicone here, and then basically to, you know, get your desired diamond. I shared this last week, but this is not happening in a vacuum. There's algorithms, and I shared this before. Fermilab, NYU Langone are working on making better MRIs. And if you read the article, it's quite interesting. Read it all the way to the bottom. BMC with algorithms for CT COVID, MIT. This is a big one. This is dealing with reconstruction. So basically the second step, which I'll show you again. And then you also have NSF. You know, they say next year, practical quantum computer, Xanadu. They did a task in June of this year, 36 microseconds instead of 9,000 years. Quantinium, better error correction. And the US Naval Research Laboratory says that we will have a national quantum internet. Harvard AWS within the past couple of weeks announced their Quantum Networking Research Alliance. And then Fermilab and Argonne, they said this year they did simultaneous classical and quantum data all at the same time. So here it is again. And when I talk about these things, as far as like, you know, with data acquisition, we talked about sensing. That's the big thing. And we're talking about raw data. So the whole goal, especially in, say, for an MRI, you can get better looking pictures if you have stronger magnets. But if you could utilize quantum technologies, especially computing algorithms and sensing, is that upfront getting the better data? Why not make MRI smaller if that's possible? So reconstruction is basically the MIT article in all this. This is, you know, neuroimaging, medical imaging. You know, basically they say they have these algorithms. It's just we need the hardware, the computers, and those two make up image formation. So then again, you have image computing, which is more visualization, analysis, these types of things with computing. So many different areas of approach, you know, with emerging quantum technologies. Now, the chemical Q device mission statement is to improve neuroimaging techniques utilizing quantum technologies for better sensitivity, signal strength, and/or resolution, leading to advanced prediction in neuroradiology for Alzheimer's disease. This includes quantum sensing, quantum algorithms, and computing for MRI, PET, and/or CT neuroimaging techniques. And then I'll take, so this is basically the summary of what we went through. I'm just, because we've had some very good discussion these past couple times here. And then, so we'll take back here. Yeah, any questions? See Philip's on as well. So anybody new that we haven't heard from? Any questions or comments, or feel free to unmute yourself. So go ahead, Philip.
Yeah, with the use of diamonds, I'm imagining that diamonds are just an excellent insulator. Is that why they're starting to be used for several applications, including farm applications?
Yeah, I mean, for the biological, it's definitely that they're inert. You know, it's not much reacts with carbon at room temperature, or say 37 degrees Celsius. They're just, they're hard structures. They're harder than other things too. But yeah, I think that's the main thing, is that, basically is like using it for anything. You saw the EV batteries with the 2 diamond quantum sensors to the rat's heart, and then, using it for this CPMG kind of the sequences as well. It's versatile. And like I said, the only warning that seems like it's out there is that if people start to switch to other things besides nitrogen, like silicon, there's phosphorus, but it just depends on what type of quantum interaction it makes when it has that they're basically impurities in carbon networks.
Okay, so is a diamond simply a more pure carbon network? Could you elaborate on that a little bit?
Oh yeah, well, you have diamond, which is super stable. You have graphite, graphene, all these types of things. And then in nature, there's impurities that actually give it the luster. So there's carat, cut, clarity.
I would imagine, aren't they probably using lab-made diamonds for the most part, perfect diamonds for their applications?
You're saying, are they using only perfect ones?
I would imagine, aren't they using lab-created diamonds?
Right. Yeah, there's
quality.
There's a couple techniques, and basically it's a company. It's called Element 6, and then this company has been associated with Nature before. And I think they actually, with the creation themselves. Now, I shared that ACS article as far as how to make your own membrane, for the surface of the diamond on your own. But yeah, the whole part is it not to be pure, is you don't want 100% carbon. I have heard that you can take diamonds and then you blast out a carbon, insert nitrogen, and then you do another step to get the vacancy. Do it that way. But as far as I know, it's all kind of like, how I shared that one diagram where it's like carefully, mixtures of, specific elements at specific times. And you saw rubidium, and you saw the PDMS, and the other polymer too. So, but yeah, they've been around for over 20 years, and the government, has been improving them. It's probably taking longer to get the algorithm to be able to sense what's coming off the red light with fluorescence to a greater degree.
Thank you.
You're welcome. So anybody that we haven't heard from? See, we have a bunch of people from last time. I think Martin was on last time, and Ron. And then Lorraine, it's great to have you on. Do you have any questions? It could be any questions. And then Dave is on too. So Dave is super into the high-tech stuff. And I would say that this is where we're at, Dave.
Yeah. Kevin, do you know Matt Swain of Quantum Insider, formerly Quantum Daily?
I don't think I ever spoke with Matt. No.
Okay. Do you know of him?
I think I spoke with one individual over there.
Okay. So he liked your post.
Oh. Awesome.
And Yeah, so there's so I know Matt, and he's really into advanced science fiction sounding applications of quantum.
Yeah, quantum imaging is the place to be for that.
Yeah, and what you're describing has gone beyond my casual understanding. So it's been an eye opener. Your medical background is showing 2 points. One is there is probably an interest at the Quantum Insider publication for this level of application. If and when you're interested in that, I'd be happy to say, hey, Matt, give Kevin a call. And if you haven't been interviewed or asked for an interview, when the timing's right, that's something that I think he would be open to. It's number one.
Yeah.
Go ahead.
Well, I appreciate it. Everything's just medical now. I mean, I still keep in touch with all the quantum stuff, but it's just everything's Alzheimer's, medical, sensing, whatever it takes to get the best images.
Yeah, no, I mean, you're unique in bringing these practical applications and providing a scientific paper level abstract, even in your descriptions. So I mentioned that before. So the time, whenever you think the timing is right, I'm happy to facilitate that. The second thing I wanted to mention is I was invited to a medical, non-quantum medical meeting. Let me just pull it up. And I'm curious if what you're doing can relate to it. It was, how can RNA be used to target multiple metastatic cancers? It was by the Michael Dudley, the CEO of, I didn't write down his company name. So they have a advanced application, and I think they're about to go into human trials for that. I don't know what the application is to quantum for it. I was introduced during the webinar earlier today, and I mentioned quantum. I don't think Dark Star is ready for that level, but we do want to facilitate and put more appropriate and wiser people in touch. So at least this Harvard PhD, actually 2 Harvard PhDs who founded the company, to be aware of what you're doing, and for some point in the future to have a demand for your skills and your IP.
Yeah, like I said, I'm getting offers too, and it's just like I can't travel all over the world. So yeah, it just comes down to putting these things down on paper, and then the schedule and that kind of stuff too. I'm happy to say that I'm dealing more with the university here, and then there's an incubator here as well, as like a really big incubator that invited me for like a full day kind of thing. So in person. And but yeah, like I said, it's all good news. As far as the RNA to metastatic cancers, everything gets really specific. Are these analogs? I imagine insertion, but we could definitely talk more about that.
Okay. Yeah, let's have a conversation after the fact. I'm aware that you get approached. So what I want to do is, if there's interest, just facilitate that they approach you with a check. The amount of work that you've done is really incredible. Your dedication is wonderful, and there are organizations. I think organizations who ask for your time, ask for your expertise, should do so with a thick pocketbook. I'd like to see that for all the quantum ecosystem around here. But anyways, I just wanted to share that, and thank you, Gabe, for putting on tonight.
Yeah, I appreciate it as well. So next week is likely going to be it's AI radiology and AI neuroradiology. It's a very established field, and this is basically using AI to get better images in hospitals. CT, MRI, PET, those types of things. So that's where that's going. Any other questions? I haven't heard from Ron yet. I think you could go ahead, John.
You're waiting for Ron or waiting for me?
Oh, go ahead, John.
Oh, okay. No, I just brought up a couple of papers based around what Dave was saying. What I'm looking at is I was on something today in Thailand that was talking about using these quantum sensors in order for CO2 capture and study. But my interest is basically looking at electrical signals without interfering, looking for storms. Okay, and that's what I'm kind of focused. In 2018, I was at a brain conference, and it dawned on me that epilepsy is a storm. Okay, in a certain part, and there are 65 million Chinese. This were the Chinese delicacy, Chinese group of I guess doctors there, and it's just brought up to me about that. They usually use surgery or drugs to suppress this point in the brain where this happens, but there's to me everything. Their understanding of it wasn't fully, because eventually they end up cutting this section of the brain out. Okay, they can't heal it, so essentially. So the idea is using these things to detect frequencies or harmonics that you can detect at a lower, say if it comes off as a C or whatever, whatever frequency you want to have, and change that over non-audio. Essentially, it starts at a lower frequency, and then by the time it hits that crescendo of the storm, then the person basically, it causes such a short circuit that takes the entire individual down. So that's what I'm kind of like hanging out looking at these sensors, because I was bringing up the sensor conference this morning. There's a company in Britain, or actually they have a technology hub that they're looking for people to come and talk to them and see what they do, because they're producing apparently a lot of different types of sensors. So something for reference. I'll find the actual link and I'll send it to you so you can disperse it.
Yeah, I appreciate it. And when you're saying that, it just reminds me of, like, keep in mind with all this, we've gone incredibly far with conventional computing, conventional techniques. As far as AI and imaging and everything else, it's just a matter of finding the weaknesses where we can't go anymore. And it could be like ghost imaging, substrate noise, quantum sensing, less of the other one. But yeah,
AI is a tool. I mean, essentially, if you've seen something, one of the guys was putting one of the crypto guys was putting something up there about how AI went through a contest and made this imaginary world that is just really gorgeous as far as they won a contest. And people are pissed because it's somehow equaling whatever it was putting together equals somebody's creative brain after a period of time. If you've ever seen some of those fantasy screensavers, right? They're really beautiful. Well done. Yeah. So for enhancing this kind on the fly, that's what I see. And then basically trying to have the thing eliminate bias. So when it's actually viewing this stuff, we're getting post-Watson, because Watson gave us all the information, I think, in the testing, whether Watson continued on for MRI imaging. At this point, I think now adding to Watson legacy and with AI coming in, to me, it's all passive, and if you can't get down far enough, then you can get the AI to say, if you have to go into these sub frequencies to figure out exactly where this thing starts, because somewhere it starts. I mean, something just doesn't, we're also at a certain frequency as it is, normal humans. And at this point, detecting something invasively or non-invasively in the brain is the only way, similar to what we're arguing with quantum, that you can't, if you view it, you can't really see it. But the idea is with the brain, you have to be non-invasive because you disrupt the brain by putting any kind of physical sensor in the brain itself, even though it doesn't supposedly feel pain. The issue is that the brain does sense activity about disturbances, I guess, in the force. Going off on that. But I mean, this way, what I'm looking at is seeing exactly, as you're looking at the neural transference, because there's as I brought up, I sent out to you at LinkedIn, there's that encapsulation from a signal to a chemical signal to encapsulation, then shooting across the synapse, and then reconstruction of the signal without loss or degradation of data. So essentially, and these are just for like basic movements of the nerve to a muscle. But then again, we start talking about how this jumps to synapse when it comes to thought, and basically we're just moving up to different levels without going into any esoteric metaphysical side, just how does the brain process all these things, since it's these types of nerves that process motor function, as opposed to the specialized cells that actually give rise to either not consciousness, but physical and analytical thought.
Yeah, I mean, it goes back to even when I first started quantum technologies for specific tasks that take too long, for quantum sensing, the same kind of thing. And then for new tasks that we can't even imagine before because we're thinking of it, in a conventional way. Those types of things as far as taking that to the next step. And right, like you really have to understand everything. So a couple people we haven't heard from, Martin or Ron, go ahead.
Hey, Kevin, had two thoughts or two comments. This was new today, finding out about the no contact or non-invasive voltage sensing capability. That's very interesting and probably has endless places to go with development there. But it kind of makes me realize that not only, in the case of medical quantum sensors, not only do you need to have a good understanding of the biochemistry involved, but looks like I'm going to have to go back and refresh myself on the electromagnetic spectrum and the orthogonal relationship of electric fields to magnetic fields. So thanks for that.
Go ahead.
Go ahead.
Well, I actually took a double dose at the university, and then I taught it a lot. So I literally, before you teach students, you really want to understand in your head what you're doing before you write anything on the board.
Yeah, my education on that goes back a ways, so it's going to be fun to get back into it. But because my education is all about how to build antennas, so for RF and stuff. My other comment was I found you, and I'm not sure if you showed that slide in previous sessions, the slide of the rat underneath the quantum sensor. There's a telltale bit of information in there that it does appear that they are using an array of diamond sensors, and it sort of suggests that the sensors are sensing lines of magnetic force perpendicular to the sample. So I just thought that was very interesting, and it makes a lot more sense understanding how you would get an image out of that sort of setup. So that's pretty cool.
Yeah, I mean, it makes sense. I took physics in school too, and it's the right-hand rule. So you have electricity with your thumb, and then your hand like this. The magnetic field's going like that.
Yeah, the magnetic field and stuff is what people usually remember, but it's the relationship of the electrical field. It's orthogonal to the magnetic field or something along those lines. So having the ability to detect an electrical field is kind of a cool thing. I'm not aware of any other type of sensor that does that, especially if it's a static field.
Yeah.
that isn't in motion or something.
Yeah, and even going back to what John said, is basically the trend is in MEG, magnetoencephalography, instead of EEG as far as the studies. Now, all this started off with a thing called SQUID, MEG, these superconducting sensors. They're the best in theory. However, they take liquid helium, and they can't be placed close to the skull because of the temperature. So that's the huge drawback. So then OPM MEG, optically pumped magnetography, and then the diamond quantum sensor. And the trend is going from the most powerful with the least results theoretical results because it's too far away. And to the diamond quantum is the least signal to noise ratio, but it can be closer to patients. Now the goal is to get the diamond quantum sensor up to speed to like an OPM. It may never get to like a squid because squid is superconducting because of temperatures, you know, all that kind of stuff. But it has larger vectors because it's closer to the skin.
Absolutely, and it's just I think the future growth of that is just going to be how densely they can pack these diamond vacancy sensors into a matrix or an array, and given that the scale of the thing is so small, should be able to go much farther than the technology we currently have for imaging. So
yeah, and
it'd be fun to watch.
Yeah, I think they're actually using it for CT. I was watching so it's computerized tomography. It's X-rays shining through a human, and then you capture what goes through them. And they said that they're using diamond sensors, and then I think they're in arrays. So that might be a use case right there where they're actually out there.
Yeah, but I mean, if you could fabricate a diamond sensor one atom at a time, think how dense you could get the vacancies. In terms of, I'm not sure how they're making the vacancies or what they're relying on currently, but that becomes very tiny, a very small or tight resolution. So it'll probably far outstrip what we currently have for imaging technology, which is more of a macro scale type of thing. This is going to be very interesting to watch.
Yeah, indeed. Martin, do you have anything? And then if not, so it was the first day of UC San Diego school out here for the college students. And lots of activity. I met with a professor I've met with before, but it's so strange. It's just like I've been waiting all summer for this. If you've ever done a startup, you want summer to end because you'll be working, but not too many other people. Well, not the bulk of the rest of your crowd that you need. So yeah, very interesting. So any other last questions or comments? Then if not, thanks everybody. This episode 49. Like I said, next week will probably be the whole AI and radiology. It's actually probably what I've been looking for from the beginning, to be honest, because that's where we're talking about the cleanest images. I saw one paper and I didn't have time this week to take a look at it, but there's at least like 15 companies. They're not all brain or like neuroradiology. They're all kind of different, parts of the body. So, but yeah, it's been thought like, so AI plus quantum technologies, it's lots of hybrids and very rarely just like a pure quantum sensor. So awesome. Well, thanks everybody for coming on. Have a good rest of the day. And then hopefully I'll see you next week.
See y'all later.
All right. Have a good weekend too. Take care.